This tutorial deals with the classification of unstructured documents using transfer learning with BERT. As a brief context, we use public consultation documents from the recently enacted Digital Markets Act of the European Commission. What we want to do is classify these documents according to whether the stakeholder who submitted them agrees or disagrees with the DMA proposal. To start the tutorial, we need to install different software requirements and dependencies, and we do this by including a YML file. These are all the libraries that we will need throughout the tutorial, and we have grouped them according to which section they will be needed. For the data, we basically need the text, which comes in the form of the PDF files, and corresponding labels. These labels are extracted from a survey that was answered by stakeholders, and this can be downloaded in the DMA consultation page. We do a bit of data cleaning, particularly for the labels. We import the survey responses into a data frame and use this to determine how many respondents also submitted a PDF file. This is the question that we will use as the label. And all those who answered yes will be classified as agreeing to the DMA proposal, while those who answered not applicable or no will be classified as not agreeing to the DMA proposal. For the methodology, we walk you through the step-by-step of the text classification pipeline, which includes data preparation, text representation, model training, and model evaluation. For the data preparation step, we start with parsing our PDFs using the PDF Miner library. We create a data frame which includes the information that we need from our text, including the raw text, which is extracted using this function. This is then merged with the data frame containing the survey responses. We remove the duplicates and keep only the submissions which have both the PDF file and a label. For the cleaning and pre-processing, we apply these steps. This is what the original text looks like after it is parsed. And we start with removing stop words, punctuations, and numeric characters using this function. We also lowercase all of our tokens. Next, we move to stemming and lemmatization. This retains only the root words and reduces them to their dictionary form. As an optional step, we also conduct corference resolution to link multiple mentions of an entity. Finally, we apply language detections to subset documents that are written in English. So our final corpus contains only 75 public consultation documents. And this is what the final text looks like. For text representation, we discuss two main ways: basic vectorization and distributed representations. For basic vectorization, we demonstrate here how to convert our corpus into a TF-IDF matrix that is composed of 75 documents and 10,527 words or features. For distributed representations, we take the pre-trained GloVe from the NLP Stanford website and use this to construct a document embedding matrix that is TF-IDF weighted. To do this, we first load the GloVe embeddings, and we see that it has a 400,000 word vocabulary, each represented by a vector of size 100. Next, we find the words in our corpus that is also present in the GloVe embedding matrix. And here we find that there are 6,487 features that are common with the GloVe embeddings. We assign this to a unique ID. And then we multiply, using the common features only, our TF-IDF matrix by the GloVe embedding matrix in order to come up with our document embedding matrix with dimension 75 by 100. This is the final representation of our corpus. For model training, we compare three different types of text classification models. First, traditional machine learning classifiers like logistic regression and gradient boosting. Second, deep learning models, which use sequence architecture like LSTM. And finally, transformer-based models like BERT. For our baseline model, we start by splitting the data into train and test sets. For this logistic regression, we use the document embedding matrix, which we constructed as our input. We then fit the regression model save the results, and also print our metrics. We do the same for the XGBoost model. And we move on to the long short-term memory network. We included an RNN in this tutorial because they were the go-to models for language processing before transformer models became popular. So they're also able to handle long-term dependencies in text. As with the baseline models, we start with splitting our data into train and test sets. However, for this model, we use the raw text and allow our model to learn the embeddings within its architecture. After splitting the data into training and test set, we build our corpus vocabulary by tokenizing the words, and then creating a function which gives us batches of text sequences that are mapped to unique indices. These sequences are also padded, so we get the sequences that are of the same length. The output of this function is a tensor, which will be used for our LSTM classifier. Here we define an LSTM classifier with the following architecture. We have an embedding layer of 200 dimensions, 80 input features, and 3 hidden layers. Next, we create the functions which trains our model and saves the weights of the model with the lowest validation loss. And here we have the results of our LSTM classifier. The final model for this tutorial is transfer learning with BERT. So in the last 4 years, this new NLP architecture has gained traction, and it has increasingly been used for different language processing tasks. Similar to the LSTM, we split the data into training and testing, and we also use the raw text. Next, we import the BERT model and BERT tokenizers. There are 2 models that are shown here. The first is the base BERT model, which is trained on book corpus and English Wikipedia. And the second is legal BERT, which is a model with 12 layers and 110 million parameters. Legal BERT is trained on a diverse corpus of English legal text. And we use this for our text classifier because DMA public consultation documents were written with the context of legal text. After importing the models, we tokenize our sequences or sentences. As we know, there are 3 embedding layers in BERT, unlike other deep learning models which only have 1. So we have the token embeddings, segment embeddings, position embeddings, and these 3 taken together would form the input representation of our text. This is an example of how BERT tokenizes the text. We get 3 different types of output. First is the input IDs, token type IDs, and attention mask. This represents one of the embedding layers. We then tokenize the entire training set and the entire testing set, and we convert these sequences into tensors that will be used by our BERT model. For the BERT architecture that we used, we take all of the weights of the BERT pre-trained model and freeze all of its layers, and then we add a few neural network layers, and finally a softmax layer at the end in order to convert our output into probabilities for binary classification. This method defines how to freeze the layers and keep all the weights of the pre-trained BERT. And then here we define the methods to train and evaluate the model. This shows us the result of the BERT classifier. For model evaluation, we compare the results of our 3 text classification methods. We print the classification report, and for logistic regression, we find that it has an accuracy of 57% and a precision of 59%. For the LSTM, it has a slightly higher accuracy of 65% and a slightly higher precision at 73%, which is also higher than its recall score of 60%. The BERT model performed just as well as the logistic regression with accuracy of 57% and slightly worse in terms of precision, but it did well on the recall. For the results of this tutorial, we want to emphasize that aside from getting a model with high accuracy, we also care about a model that minimizes false positives and maximizes precision. So with that criteria in mind, out of the three models, we find that the RNN-based LSTM currently works the best in terms of both accuracy and precision. We note, however, that we have not yet conducted hyperparameter tuning and any further refinement of our models, so this result can still very well change. We have noted down some limitations of our models and also next steps for future research involving data collection, pre-processing techniques, modeling, and other applications of text classifiers.